Hey, welcome to this demonstration of the AI that I've been working on. It is based off the finite state machine that has been put together by Gitterman from YouTube. His finite state machine is very well structured and documented. So yeah, gone with my implementation of it, leveraging everything that it does to make this enemy do what it does. So, what is it? Or rather, what does it do? It's got this cone that is its line of sight. It's got the red radius, which is its attack distance, where it actually performs an attack, and the magenta radius is where it will then begin the attack approach and the attack, I guess, strategy is probably the word over there. So currently it's just following a patrol. It can wander if there is no patrol pattern given to it, but for now it does have a patrol. So actually what happens, we're just going to quickly move our player. You can see we're in range. If you look at the log down below, he's now chasing us. He's in attack range. And he's going to come up to us. He's going to try and attack. And he's also going to be doing some strafing around us. So yeah, that is essentially what it does. We are actually being hit. We are being attacked. We will die if we do not move. So in this case, I'm just going to try and run away, run out of his line of sight. And he has... Oh, just couldn't get it quite there. Yep, there we go. We're out of line of sight. He's gone back to patrolling. That is basically the entirety of that enemy. So how does it actually work here? Just going to stop that over there and put this aside. So very simply, the enemy has got a suite of sensors and he's got his logic that or the finite state machine that determines his behavior. He's got an agent for moving, an animator required for now, but you don't need to populate any animations, at least for the time being. The reference to sensor suite, the target, in this case I called it player, but that should actually be target. Some patrol parts. These patrol parts you can see, this is what he was trying to follow when he was not attacking. And then we have the wander radius. If he doesn't have patrol paths, they're just going to wander around in some radius, and time between attacks, which is how often he attacks. So he uses a finite state machine. Let me quickly jump in and show you exactly what is going on. Actually, probably one step back. The sensor suite is actually what he uses to determine conditionally is something within range, is something within line of sight. Everything is hooked through the sensor AI, and it has a reference to the line of sight sensor, completely configurable. We've got some gizmos that we're just drawing so we can visually see what's going on. And yes, these are just some of the sensors. So how does it actually work then? The sensor suite, so the sensors are, they all derive from iSensor. The sensor AI has got a list of every sensor. For example, the attack range sensor, it is an iSensor. What it does is basically goes through every single sensor and performs the evaluate function. You probably saw there on the interface iSensor, it forces an evaluate function to be created for any given sensor. We can then get any sensor of a particular type whenever we need to retrieve some values from within that sensor. This allows for a very robust approach. We can just throw as many sensors as you want at it, so you don't have to think about, okay, do I need to then add that sensor to the list so then I can get it, and you don't have to do a list check every time that you want to retrieve that sensor. So our enemy, this is what drives it. It is just a monitor behavior. Think of entity as just monitor behavior. It's got our agent, animator, sensor AI, everything that we just saw. Attack range. Sorry, that is just a reference to a sensor. Yeah, a cooldown attack timer. So whenever it attacks, there is a certain amount of time before it can attack again. That doesn't mean that the attack logic doesn't stops. It just means that the actual damage that happens is on some kind of timer. Very simply put. So first we're going to initialize our state machine. And the state machine, so if anyone's seen Gitterman's video on the basic AI state machine, this is pretty much it. Just fully utilizing what he was actually talking about and what it's capable of. So first we're going to instantiate a new state machine. We'll get into what that is in a little moment. We've got some states. So everything that, think of it as actions. So when you're in a state, it is performing some kind of logic continuously until it changes state. Over here, we've got wander, chase, attack, patrol, and we're feeding it some very basic parameters. Then we've got define transitions. So transitions are actually the powerful point, and this is what determines what state we go from and go to, and that will only happen by some kind of condition. So in this case, if we've got a chase state, we go to a patrol state. If the condition is our sensor for line of sight has got no target, or rather is target in line of sight, it will perform an evaluation through the sensor AI, and it will return a boolean that says yay or nay. So in fact, I probably should have mentioned earlier when going over the sensors, every single sensor does one specific thing, and we try to keep it as narrow as possible. And it will always evaluate a single boolean. You'll always get a yes or no. There is no conditional, or rather there is no multiple boolean returns. You don't get an object. You always just get a boolean yes or no. So that is one of the paradigms behind the sensor. So let's go back here to the AI. So like I said, we have a from state, a to state, and the condition that must be met for this state change to happen. Now there is also an any transition that takes whatever state you're in, go into the target state based on this condition being met at any time. So it's very important to keep in mind, because you can actually add more conditions as well to this to keep it very narrow, or you can keep lower amount of conditions, such as this. When we're in range, we start attacking. So very broad. The important thing over here is that it doesn't require a from state, so it'll always interrupt and go into the state. Then lastly, we've got the initial state that we're going to set it in. In this case, well, you might have seen earlier, and over here, we're just conditionally going into a patrol state if we have patrol waypoint set. Otherwise, just wander around aimlessly if we have no patrol waypoints. So that was also what was here. Go from wandering or patrolling into chase. Go from chase to patrol. Go from attack to patrol, or from anything into attack. This is where the sensor suite comes in very handy, is that we do have all these conditionals to help us determine when something should happen. The at or any is actually just based on these helper methods that we're going to see in just soon when we go into the adding transitions. It's just very shorthand for making this look clean and understandable. On the update, we're always going to make sure that we take up the state machine, or we're going to run the state machine's update loop. We'll get into what that actually means. We have a timer. Remember the cooldown attack timer. We have to tick it by time.delta time on the update, and the attack logic that says while on cooldown, do nothing, otherwise attack. So let's jump into the very basic, which is iState. So if all states derive from iState, we've got our enter, update, fixed update, and exit. And what does this actually mean is that these are the different points of activity in a state when we're trying to determine the logic. When we enter, then update or fixed obviously for physics, and on exit when we're exiting the state. More on that in a moment when we do look at the state machine. What does an actual state look like then in this case? So we've got our iState. Now we've got our enemy base state. Think of enemy as like any kind of entity that you want to have some kind of behavior. Set up a base state for it, which derives or inherits iState. It's going to force us just to implement the methods, the core methods for it. We're not going to do any logic here because we actually want the actual state that we're going to be making to define the logic. For now, we're just doing a little bit of setup, an animation, a reference to an enemy, and a reference to the animator. So let's actually go into a state. Let's go into the wander state. This is the very first one we default go into. It derives from the enemy base state, and this is where the logic begins. We have a basic constructor, we have the standard constructor plus a wander radius we've added in there, and we're just binding it. On enter, we're going to say that we're wandering. In fact, on enter is a good location to then perform any animations going into this state, so we can crossfade from wherever we were animating into this by some kind of duration. Then in this case, because we're wandering, we're just going to look for a valid point and set our agent to it. I think this is probably a good part to talk that all the movement is being controlled through the agent, so we're always dealing with the agent and not a transform dot move towards or anything that's going to force a transform to move. We're letting the agent to determine the location to move to, and it will find the best path possible. It also means that we can clear the path or do anything to the logic of the agent. Probably more specifically, I should have mentioned that is a nav mesh agent. So we have some logic, and when we leave the state, it'll perform just a reset of the paths. So in this case, for the state, we're resetting it so whatever picks up or whatever state we transition into, the path is reset, and it is still not trying to go towards a location while starting in another state. We like to always keep it clean before we enter another state and let the state determine what to do next. Obviously, this is one way of doing it. I think actually putting more thought into this, maybe resetting is best on enter, because we may be coming from a state that does not do any navigation logic. This is just willing to check if we've reached the destination. So that is the wander. We'll quickly just jump into the just another one, say the chase state. When we entered to it, remember we went from wandering to chasing. So our logic is go from wander into chase, or patrol into chase, when the enemy's in line of sight, or rather when the player's in line of sight. So if we were then to chase, you can see it's the same thing. It becomes a very common way of looking at it. We enter, we do something, and we have some exit. You don't have to use all of them, you only use what's necessary. So how does the enemy then determine actually what what the condition is. So we've got our sensors, and they are all being fed into what is called a predicate. So a predicate is something that just returns a Boolean after running some kind of evaluation. So a function, or rather an predicate in this case, just returns a Boolean of evaluate. Running the evaluate method, it returns a Boolean, and our func predicate basically feeds in the function that you have seen earlier in the sensor being fed into it. It returns its returns Boolean. So in this case, we're just invoking whatever is being fed into this. Next up, we have transitions. So transitions, let's just go back to enemy. So the transitions, as we've seen, how does this actually work? Remember, there are these helper methods that just short form adding the transitions. The actual transitions start from a I transition, just to give you a to and the condition. And we've got the transition, which is just a wrapper. Not a wrapper. It enforces the I transition interface. Once again, just to and some condition. And this is all tied together by the state machine. The state machine, this is where all the magic happens. It holds the current node and every node that we fed into it, as well as all the transitions to and from those nodes. So it knows how to go between them and how to handle the conditions that allow it. There is once again now update, fixed update, update, fixed update, and our transitions that perform everything, because the state actually then says, hey, you've started the state, perform enter. Then that is when the after the enter, the state machine takes over and performs update and fix update. And when we exit, we run the on exit. Actually, sorry, that is I'm a little bit mistaken there. I think I'm starting to lack a little bit of sleep, but essentially we have update, fix, update, and when we are changing state, we actually then have our exit of the previous state to run and the enter of the next state. So that's how it works. The get transitions, we will always first get the any transition. Because it's an interrupt, we want to evaluate the interrupts first before we go to the actual transitions of the state. And here are some of the methods to enable us to add a transition or add an any transition. Remember the at and any that we saw earlier in the enemy? At and any, it's just a wrapper with this helper method that actually just runs at transition, at any, and at any transition is just a short form, so we can easily do this. So yes, that is basically the state machine and how it works. Obviously, all that is just for this enemy. This enemy can be, you can then say, okay, rather than just calling it enemy, we can call this maybe a ranged enemy, and we can do a new one for a melee enemy that has different values set up for, say, its line of sight, or different attack ranges, because it's a ranged enemy. Versus a melee enemy. So we can set up very different profiles with this already without having to change much. And we can add more transitions. Say, instead of going from attack back to patrol, we go from attack to a search state, where the enemy is gonna stand in place and look left and right and determine, okay, well, I guess the player is gone. I will then go from the search state to the patrol state. So there are many ways that you can extend this. Obviously, there is a certain complexity limit where you start having this many-to-many relationships, and it just becomes very hard to determine what transitions to what, and all the various interconnects. So those relationships only get more complex the more states you have. A finite state machine is not a behavior tree. In fact, a behavior tree is what solves the multiple complex conditions and states. So yeah, this is the finite state machine, and hopefully you've got something out of it. And lastly, just real quick, for those that haven't seen any of the previous videos, I will just quickly open the patrol part. It's just a gizmo, and it checks whether it has any assigned nodes. Very simple. That is just so that we can visually see where we are patrolling. Anyway, thank you.